Hello everyone, welcome to Analog Electronic Circuits lecture number 14. So today we are going to solve a numerical on a cascade amplifier. So let's begin. So numerical reads that a two-stage circuit is shown below. Find the input resistance of the circuit, output resistance of the circuit, and voltage gain of the circuit. So the BJT parameters given over here are beta 1, beta 2 is 220, VB1 and VB2 is zero point 0.7, and this is the circuit given to us. Okay. So looking by the looks of it, it's like a two-stage common emitter cascade amplifier, right? All the resistor values are given. R1, R2, RC1, RE1, then R3, R4, RC2, RE2. There is no load resistance, neither there is a RC internal resistance of the source given. All the coupling capacitors values are given to us, and transistor Q1 and Q2 are connected in a cascade fashion. So we have to find R in, R out, and voltage gain for the circuit. So let's begin our analysis. So one thing, if you notice carefully over here, both the stages are symmetric. If you look carefully into the parameters again, okay, let me bring it over here. R1, R2, R3, R4 are same. RC1 and RC2 values are same. RE1 and RE2 values are same. Also, the the transistor parameters of both the stages are also same. So I guess both the stages are symmetric, we can easily say, right? And since they are, we have used over here RC coupling scheme, the Q point of first stage won't disturb the second stage. So that means if I find a Q point for one stage, the second stage Q point will also be the same because all the parameters and the register values are same. Okay. So first of all, whenever you solve this numerical, first step is to identify which circuit it is. So we can write the above given circuit is a two-stage RC coupled common emitter amplifier, cascade amplifier we can write. So very important first to identify which is the cascade stage over here. Okay, cascade amplifier stage. Okay. So now next step is, since we are identifying that both the stages are symmetric. So next step we'll write over here, due to RC coupling, the Q point of both stages, due to RC coupling, the Q point of both the stages are isolated or independent from one another. Okay. And also third, one more statement we can write over here, that since both stages are symmetric, in parameters and register values, the DC stage of one stage is sufficient. Okay. The DC analysis of one stage is sufficient. We can easily say, once we find the DC and the Q point for the first stage, the Q point for the first stage is equal to the Q point of the second stage. Okay. So let us start with the DC analysis. So we'll start with the DC analysis. Okay. And for the DC analysis, we'll do the DC analysis for one stage. So for the DC analysis, all the capacitors are open circuit. Okay. And we'll consider the first stage. So let's do that quickly now. So we'll do the DC analysis of the first stage. Let me quickly draw the circuit over here. So here we have R1, R2, RC1. So here we have this. Supply voltage is VCC, and we have R1, R2. This is ground. This is RE1, and this is RC1, and this is Q1. So we have to find a Q point for this. So first of all, we have to find the value of VTH. So what is VTH now? VTH is R2 divided by R1 plus R2 into VCC. So what are the values of R2? R2 is 2.2K, R1 is 22K, R2 is again 2.2K. And I think VCC value is given as 15 volt. Okay. So plug in the values in the calculator and you will get VTH is equal to VTH will be equal to 1.364 volt. Okay, so that's the value you get of VTH. So I'm marking it over here, highlighting it. Okay, so we got the value of VTH. Next, we have to find the value of RTH. RTH will be R1 parallel to R2. And what's the value of R1 and R2? R1 value is 22K, R2 is 2.2K. Okay, so find out the value of RTH. If you calculate in a calculator, the value of RTH will be 2 kilo. The value will be 2 kilo, so I am highlighting it. Okay, so after this, we have to find the value of, let me mark over here, step number A, B, and C. Now, once we know the value of RTH and VTH, we have to find the value of IBQ. Okay, so let me do that. So next step is IBQ, IB1Q, because it is the first stage. So it will be given by VTH minus VB1 divided by RTH plus 1 plus beta 1 times RE1. Okay, so over here the value of VTH is around 1.364, VB is around 0.7, and RTH is 2 kilo. So 2 into 10 raised to 3 plus beta is around 220. So this will be 221. RE1 value is around 150. Okay, so plug in the values in a calculator and you will get, I'm sure that you will get the value close to 18.89 microamperes. Okay, so that's the value of IBQ you will get. Fine. If you get any different answer than this, please write it in the comment section. Now, once we know the value of IB1Q, we'll find, okay, to select a black pen. So next we'll find the value of IC1Q, which will be beta 1 times IB1Q. Okay, so that will be 220 into 18.89 microamperes. And if you work it out, this value will be 4.156 milliamperes. Okay, so that's the value of IC1Q. Okay, now since both the stages are symmetric, we can write that ICQ will be equal to IC1Q will be equal to IC2Q will be equal to 4.156 milliamperes. Okay, so that's an important step. We can conclude from here. Okay, so we have calculated the DC parameters. Next step is evaluation, estimation of small signal parameters. So that will write step number 5, small signal parameters. Okay, small signal parameters. Okay, so from here we'll calculate what are the parameters of of a BJT. The first parameter over here is GM. So we can find GM1, which is given by IC1Q divided by VT, right? VT value is 26 millivolt IC1Q value is 4.156 milliamperes. So accordingly, the value of GM1 will be, if you work out in a calculator, it will be 159.85 milliampere per volt. Okay, so we'll highlight it. Now, since we know that IC1 and IC2 are same for both the stages, so we can write over here GM is equal to GM2, which is equal to 159.85 milliampere per volt. So this is the value of GM1 and GM2. Next, we calculate the value of R pi. R pi is the small signal parameter for BJT. So R pi 1, its formula is given by beta 1 VT divided by IC 1Q. Okay. From here, beta value is 220, VT value is 26 millivolt, and IC1Q value is 4.156 milli. So if you work out in a calculator, R pi 1 value will come close to 1.376 kilo ohm. So please cross check this answer. The value of, value of R pi 1 will come close to 1.376 kilo ohm. Okay. Now, since the beta value is same for both the stages, VT remains the same, IC1 and IC2 are same, we can easily write that R pi 1 is equal to R pi 2, which is equal to 1.376 kilo ohm. Okay, so that's the value of R pi 1 and 2 for both the stages. Fine. Now, this we have written since both the stages are symmetric. GM1 and GM2 are same, R pi 1 and R pi 2 are same. What other parameter we have for a BJT? So we should have RO1 and RO2. RO1 and RO2. So basically, we know that the value of early voltage is not given. So we'll assume RO1 equal to RO2 to be equal to infinite ohms. Okay. So we'll assume this data if the value of early voltage is not given to us. Okay, fine. Next, we have found out the value of DC parameters and small signal parameters GM and P pi, R pi. Now, next we will to find the voltage gain, input resistance and output resistance, we'll draw the mid-frequency equivalent circuit. Okay, so yeah, we will draw the mid-frequency equivalent circuit for this diagram. Correct? We can quickly draw that and then we can find out easily the values of the voltage gain and input and output resistance. Fine. So let's start and do that thing now. So I'll do it side by side over here. Which was the step over here? Let us find out. It was step number 6. So we'll follow step number 6. We'll draw from here. Okay. So this is step number 6. Last lecture we have done the analysis. Let's do it one more time. So we'll write over here mid frequency. If you know the formulas directly, well and good. If not, you draw this. It will hardly take a minute. So we have drawing mid frequency small signal equivalent circuit. Mid frequency small signal equivalent circuit. Okay, we'll not derive it briefly, we'll just use it for the reference. Okay, to quickly write down the formulas without hesitation. Okay, fine. So to draw the mid frequency small signal equivalent circuit, we have to short circuit the DC sources and the connected capacitors. So that point we'll write over here. Let me slightly yeah, I think this much is fine. Yeah, so I have to short circuit let me slightly maximize, zoom out a little. Yeah, I have to short circuit DC supply and connected capacitors So let's quickly draw the mid frequency equivalent circuit and replace BJT by its hybrid pi model, and replace BJT by its hybrid pi model. Okay, so let's do that quickly. So here is a circuit. So first of all, we have to mark over here base collector region, right? So this is base 1, this is collector 1, this is emitter 1, this is base 2, collector 2, emitter 2. Okay, so first of all, let's quickly draw the hybrid pi model for Q1 and Q2. Fine. So I am drawing the model for hybrid pi model for Q1 and Q2. So first, let me start with this is base 1, collector 1, and emitter 1. Let me mark over here base 1, collector 1, emitter 1. Similarly, I leave some space and draw it for the second stage. This is okay, base 2, collector 2, and emitter 2. Fine. Now from base to emitter we have R pi. So I'll mark over here R pi 1, and here the voltage will be V pi 1 quickly. And between the collector and the emitter we have a dependent current source, and we can write it as GM1 into V pi, right? We don't have RO1. RO1 is infinite, so we'll leave it. Let me slightly, yeah. Now let me complete for the Q2 transistor hybrid pi model. So here between the base and the emitter we'll have R pi 2. The voltage across it will be V pi 2. Between the collector and the emitter we'll have a current source, voltage dependent. Its value is GM2 into V pi 2. Okay. So we have drawn the hybrid pi model for Q1 and Q2. Next, we have to complete the circuit. Okay. So we'll look into the diagram and then complete it one by one. Okay. So over here from the base terminal, we have R1 and R2 in parallel, and then we have Vin connected. Emitter terminal is grounded because capacitor CE1 is sorted. Emitter 2 is also grounded because emitter 2 terminal is grounded because CE2 is also connected to the ground. So let's do this connection. So from base 1 we have R1 parallel to R2. That's it. And then we have a, so here it is R1 parallel to R2. And over here we have a voltage source V in plus minus. Emitter terminal of both the circuits are, of both the stages are grounded. We have mentioned the reason there. So emitter 1 and emitter 2 are grounded. Fine. So this is complete. Now let's move on to the next one. Let's see what is connected between collector 1 and base 2. So let's go to the circuit diagram. So collector 1, from collector 1 we have RC1, and then this CC2 is short circuited. So collector 1 is directly connected to base 2, and from base 2 we have R3 and R4 in parallel. Okay, so let's do that quickly. From collector 1 we have, from collector 1 terminal we have RC1, and then in parallel the collector 1 terminal is directly connected to base 2, and then here we have R3 parallel to R4. Fine. Now next is from the collector 2. From the collector 2, let's find out what do we have from the circuit. So from the collector 2, we have just one resistor RC2 going towards the ground. Oh, sorry. Yeah. So let's do that connection over here quickly. Okay. So from the collector 2, we have, let me mark over here. This is RC2, and we can call this as plus minus V out. Okay, fine. Now let me just look at it in a whole picture. So this is your mid frequency small signal model, small signal equivalent circuit for the given cascade amplifier. From this we have to find out, this is RC1. From this we have to find out Rin, ROUT, and voltage gain. Okay, so let's start. Okay, so first of all, let's find out now. Let's find out Rn. So Rn in a cascade stage is equal to the input impedance of the input resistance of the first stage. So what is the input resistance of the first stage over here? If you look into here, okay, if you stand here and look into the right hand side, we'll get R1 parallel to R2 parallel to R pi 1. Okay, so let's calculate input resistance. So that will be, let me use a black color. Yeah, so it will be R1 parallel to R2 parallel to R pi 1. Now, what are the values of R1? R1 is 22 kilo ohms, R2 is 2.2 K, and R pi 1 value is how much? We have found out to be 1.376 kilo ohm. Okay, fine. So if you calculate this in your calculators, your Rn input resistance will be 815.16 ohm. Okay, so that's the value of input resistance R in. Right, now we have to also calculate R out. Right, so R out is looking into this terminal over here. So standing over here and looking into this, so what we will see, we'll see RC2. Right, why don't we consider GM2 and V pi 2? The impedance offered by this current source will be infinite. So only resistance over here, infinite meaning it will be open circuit. So the resistance looking at the from the output terminals towards the left hand side, you see only RC2. So it's very simple. R out, it's just equal to RC2. So R out will be equal to RC2 and its value is 1 kilo ohm. So straight away, nothing but directly writing the value of RC2 will fetch you 1 marks for the calculation for R out, right? Now, next thing is crucial. Next, we have to calculate the voltage gain. Okay, so voltage gain AV, which will be V out divided by V in, the overall voltage gain, including the first stage and the second stage. So what we will do is we'll mark one extra voltage over here, which is, let me use a different color, orange color over here. So let me mark this point as V1, because this V1 is the output of the first stage and the input of the second stage, right? So if you want to calculate, let's say AV1, I mean the voltage gain of the second stage, how can we write it over here? So AV2, the second stage gain can be written as V out divided by V1. Okay, and the first stage gain, how can we write first stage gain over here? First stage gain can be written as V1 upon V in. So let me mark over here. AV1 is V1 upon V in. So basically we have to find V1 upon V in, AV1 and AV2 and multiply them to find out the overall gain. So here the same formula can be written as V out upon same expression, V out upon V1 into V1 upon V in. Whereas your V out upon V1 is my gain of the second stage, and V in upon V1 upon V in is the gain of the first stage. Right? So let's invest our time in finding out the gain for the second stage first. Always start with the second stage, right? Now, what do you see over here? V out, here we have a resistance and here we have a current source. So basically, what is the current flowing over here? IC2, and it's an outgoing current. So we can write V out is equal to V is equal to IR, right? So minus of IC2 into RC2. And what is IC2? IC2 is nothing but GM2 into V pi 2. And what is your V pi 2? V pi 2, if you look into the diagram, it is in parallel with V1. So we can replace replace V pi 2 with V1, right? So now it becomes very simple. The expression V out will be equal to minus of IC2, that is GM2, into V1 into RC2, right? So what will be the gain over here? AV2 will be given by, what is the expression? AV2 will be given by V out upon V1 is equal to minus of GM2 into RC2, right? So that's the formula. We have derived it very easily. Now we have to find the values. So what is the value of GM2? 159.85 milli. Okay, and what's the value of RC2? Its value is 1 kilo ohm. So if you multiply them, you will get the value of gain AV2 as, let me write it down, the second stage gain will be minus 159.85. Okay, so that's the value of second stage gain which we get. Fine. Now let's concentrate our efforts in finding the gain of the first stage. Over here, we'll have to find out the value of a V1. So if you see over here, V1, I mean, we have a resistance over here, RC1, R3, R4, and R pi 2. All are connected in parallel. So voltage will be, V1 will be all these resistance in parallel into the current. The current is outgoing current again. This current is called as IC1. So IC minus of IC1 into all these resistances in parallel. Okay. So, voltage is equal to V is equal to IR, right? This is a linearized version. Whenever we draw a hybrid pi model of a BJT, we are linearizing the non-linear MOSFET, right? So hence your your Ohm's law will be applicable over here. So we see all these resistances RC1, R3, R4, R pi 2, all are in parallel. These resistances into IC1, right? So that will give you the expression as follows. So we can write over here V1 is equal to minus of IC1 into those resistances we can write over here. We'll mark it. Let me mark those resistances. Yeah. So these resistance values are, let me take it slightly up. Yeah. RC1 parallel to R3 parallel to R4 parallel to R pi 2. Okay. So that's the value of, V1. And what is IC1? IC1 is GM1 into V pi 1. Actually, we should have written over here V pi 1. Yeah. So let's complete it now. So IC1 is nothing but GM1 into V pi 1. And let's see from the diagram what is V pi 1. Now over here, if you see V pi 1 is same as V pi 1 is same as V in. Okay. Here we forgot to write R in. So V pi 1 is same as V in, right? So we'll write over here, instead of V pi 1, it's equal to V1. Okay. Fine. Since V pi 1 is equal to V1. Now we'll write expression of V1 again. V1 is equal to minus of IC1 is GM1 into V pi 1, that is V1, into RC1 parallel to R3 parallel to R4 parallel to R pi 2. Fine. Now, okay, this will be V in, sorry, this is not V1, sorry, very sorry for that. V pi 1 will be equal to R in. Let's look at it. V pi 1 is equal to, V pi 1 will be equal to V in, sorry. So I've said it correctly, but written it wrong. So V pi 1 is equal to V in. Let me use the orange color. Yeah. So, okay, fine. Yeah. So now we write the expression here. It will be, instead of, this is V in, GM1 into V in. Now we can divide, by V in. So that will be AV1, which will be equal to V1 upon V in, which will be equal to minus of GM1 into RC1 parallel to R3 parallel to R4 parallel to R pi 2. Okay, so we'll get this expression. Yeah, let me mark it so that we can represent that this is which coming from the small signal, the mid frequency small signal equivalent circuit. Okay, and now we have to calculate this AV1. So what was the GM1 value? I think GM1 value was 159.85 milli. This is RC1. So what was the value of RC1? RC1 value was 1 kilo ohm. RPi2 value was 1.376, and R3 parallel to R4 is basically R1 parallel to R2 is equal to R3 parallel to R4, because they are symmetric, and that was coming out to be 2 kilo ohm, right? So this number over here will be equal to 2 kilo ohm. Fine with it? So this is the value of, we have to solve this in our calculators and find out the value of AV1. So that is AV1 will be equal to minus of, so this will be minus 159.85 into 10 raised to minus 3 into, and if you solve it, you will get this 4 resistances in parallel. The value will be 449. Fine. So therefore, your AV1 value will be equal to minus of 71.78. Okay. So let me highlight it now. So that's the value of the gain. That's the gain of the first stage, AV1. And now what's the total gain? Total gain is AV is equal to AV1 into AV2. So let's find the total gain now. This was, yeah, let's find the total gain now. D part. So AV will be equal to AV, total gain AV will be equal to AV1 into AV2, and the value of the first stage gain will be is around minus 71.78, and the second stage gain value was around minus 159.85. Okay, so if you multiply them, you will get the value of total gain as, the overall voltage gain value will be 11474. Okay, so that's the value of overall voltage gain. If you want to find in dB, then you can do that. That is, AV in dB will be 20 log to the base 10 of 11,474. So this will, if you work out, this will be like 81.19 dB. Okay, so the gain in dB of the given cascade amplifier is 81. If you want to say in terms of magnitude, it will be 114.74. 11,040 11474, and in terms of dB, it is value is around 81.19. Okay, so with this we have completed the numerical, and we have found out the values of input resistance 815.16, output resistance 1 kilo ohm, and overall voltage gain, that is 11,474 or 81.19 dB. So yeah, with this we conclude this numerical and we conclude this session. So that is all for this time, and next time we'll start with the analysis of common source RC coupled cascade amplifier. So until then, have a good day and thank you.